In the last video, we discussed the Hall effect, and before that we discussed the magnetic force on a moving point charge. In this video, we basically want to kind of lift that up to understand magnetic forces acting on a wire carrying current. So, in case you were curious, this is not a jalapeno pepper in a magnetic field. This is supposed to be a wire, and we're going to assume it has a uniform cross-sectional area A. The size of this does not indicate my poor artistic abilities. In fact, it indicates 3D depth, so that's actually skill, so you should be impressed. I know Sam, who always likes to compliment me on my artistic abilities. I'm sure she's approving right now. Okay, so the way this will proceed is we will analyze the forces on each little segment. I went ahead and marked out a little segment of length ds along the wire, and we'll kind of figure out the formula for the force on that segment, and then add up the forces for each of the segments and to find the total force. Along the way, we're going to have to review a little bit of vector calculus, and we'll review a little bit more in the next video, and a little bit more, and a little bit more, because as we get into magnetic fields, we're going to have to remember how to do cross products and line integrals and things that you haven't had to do too much for me thus far. Okay. All right, so what we have here is a current carrying wire. There's going to be current flowing, and let me do that in blue. We'll go ahead and say that the current is flowing that way. And so what we want to know is, well, okay, so remember the formula for the magnetic force on this little segment. Well, it's a tiny segment. It's a differential size segment. So we know that the magnetic force on this is going to be tiny. It's going to be dF magnetic. It's going to be dq, whatever that amount of charge is that is moving in that little segment, times the velocity, well, that'd be the drift velocity cross the magnetic field, right? And remember, the drift velocity is going to point in the direction of the current flow for this. We're going to kind of work this out, assuming that the charge is positive. It doesn't really matter that the actual charges are going the other way with an opposite charge and opposite velocity. Mentally, it's just easier to follow hypothetical positive charges, so you don't have one last minus sign reversal to do. So to figure this out, what we want to do is come up with a different expression for dq and all this thing. So what I'm going to do is think about this little segment, and I'm going to think of dq. That's the charge which passes by in a moment, in an amount of time delta t, or dt. So I could think of that as, sorry, it's not even that. It's just not in a time dt. I can think of this just as a volume times the density of charge carriers. So I could just think of this in a kind of steady state conditions. I could just think of this as the charge per carrier times the carriers per unit volume times the volume of that kind of hockey puck looking thing. Should be the area times ds. This would give you the volume. This is the carriers per volume. And this is the charge per carrier. Okay, that would give you an expression for this, this quantity right here. All right, so that's fine. Now, here's the thing. I'll come back to this in a minute, but we have that formula. But the other thing is, rather than working with ds, the scalar ds, which is just a length, you also have ds vector, which points tangent to the arc lengths, tangent to the curve. I'm being sloppy, going back and forth between cursive and Latin, or in print characters. It doesn't really matter. In fact, because this vector is along the wire, the same as the velocity is along the wire, we actually can say something kind of nice. We can say that ds times a velocity, drift velocity vector, because they are parallel, you can actually swap which one is a magnitude and which one is a vector and write that as vd, magnitude of the drift velocity, times ds vector, because both are parallel to the wire. So pulling it together, I can say that the little bit of magnetic force, which equaled Q times N times ds times the area times v vector cross b, equals Q times N times the magnitude of the drift velocity times the area times ds vector cross b. Okay, these are equal, but this is nice because this is the formula we found earlier for the current. So I come up with I have arrived at a kind of handy formula for the force on a current, the magnetic force on a current carrying segment of wire, which says that the force on a little segment from the magnetic field is the current carrying the wire carried by the wire times the arc length vector differential cross the magnetic field. And I should say ds is defined to point along the same direction as the current flows. All right, and if we want the total magnetic force, this will equal the current, which we assume to be constant and scalar, so just pulls out of the integral. The integral along the entire path of ds cross b. So that's our formula for this kind of thing. And that is generally, well, that's always true. That's true for any shape. And as usual in vector calc, for a typical shape, it's a nightmare to evaluate. But for special cases, namely when the magnetic field is constant, when the wire is a straight wire or a nice circle or a half circle, something simple, you can evaluate this and arrive at a reasonable formula. So what I want to do next is to kind of review different expressions for ds, kind of remind you of what it means, and then work out a few examples. But this is the general formula, and then we're just evaluating special cases for the rest of this video and then for the next few videos. Okay, so just a review, a Calc 3 review for some of you. So if I have a wire or if I have a curve, then I can mark out a little segment and define a vector differential, which points along the curve. So now if you thought about, maybe I should have made my wire a little bit, or my curve, I keep saying wire, it doesn't have to actually be a wire, but okay. And let me mark out these 2 points. Now if you think about that, T is a tangent unit vector, so T hat here points along the curve. ds is the arc length, and it would be the arc length along that curve. Well, if you zoom in on a tiny little segment of that curve, ds is going to be the length along the hypotenuse. But, you know, any curve, if you zoom in close enough, becomes straight. If you get really close to it, which means that when you're manipulating differentials, you can pretend that it's straight and that this builds up a triangle with ds on the hypotenuse, which I said just now with a slip of the tongue, maybe. In which case I would have dx here and dy here, and therefore I would learn that ds equals the square root of dx squared plus dy squared, or pretending that fractions or the differentials can be, the derivatives and things are like fractions, you can write this as the square root of 1 plus dy dx squared times dx. And I think that's probably the formula, or a formula you used in Calc 1, or maybe Calc 2. I'm not sure, Calc 2 or Calc 3. You could also rewrite it as the square root of dx dy squared plus 1 dy. There are different ways you can write it. They're all equivalent, and really this is the one you should remember. Now, I know we didn't ever push through with our program of math problems of the day. Just this whole thing is really throwing all that for a loop. If you go back to math problems of the day, the goal was, one of the goals was to have you comfortable with manipulating these kind of arc length differentials, and you can rewrite it using the metric function, or metric matrix and Jacobian matrices, and which would allow you to actually express this in arbitrary coordinates. We didn't get that far. This whole thing has really kind of jumbled my plans, so that just didn't quite happen. Anyway, so what I'm going to do is, so the plan was to have you go through and evaluate a bunch of Jacobians and metric tensors, and kind of work through what this would look in arbitrary coordinates and 3D or 4D, whatever you wanted. I'm going to just remind you of the special cases that we will really need for this course. So special cases involve, if you have an arc which is along the x-axis, in which case you would have ds equals dx, and ds vector would be dx times x hat, because the tangent to this would be x hat. In the y direction, you'd have ds vector is going to be dy times y hat. Those are useful cases. And then another important case that we will see from time to time is what you have when you have an arc, a circular arc. Okay. Now in that case, ds, the scalar quantity is just, sorry, I should have said this. If this has a radius r, then that's just going to be r d theta. That's the scalar arc length in that case. But ds vector then, well, okay, we have to mark a path. So let's say that we were going counterclockwise, arcing like that. Then ds vector would be ds, this expression, but then it would point tangent to this arc. Tangent to a circle is in the direction of increasing angle. So that would be theta hat. And so you would just say that this was r theta hat d theta. Just a word of warning, remember that theta hat, a polar unit vector, is not constant. It changes as you move around, which makes sense because tangent to this curve is changing at different angles. So this is not a constant. Even though usually people don't write the argument, it's a function of theta itself. Okay? So that's a thing to note. I'll kind of spell out more about polar unit vectors in another video shortly. One last little thing that I wanted to point out is that if you had any arbitrary closed path and you were to kind of break it up into little segments, and if you were to integrate around this closed path, so put that with a little arrow, an orientable closed path, ds vector. What would that mean? Well, that would mean you add up all the vectors going all the way around. So you have a little one here, a little one here, a little one here, whatever. You would add them all up. But when you added up all these vectors, they would add up to 0. So the integral of the arc length vector differentials around a closed path is 0. And that's true for an arbitrary shape, kind of as this little picture shows. You just add up all the little changes in displacement and you would get 0. So we're going to use that fact in just a minute. Okay, so that's a quick review of Calc 3, and I'll throw in a few more facts as we go along. Okay, so let's apply. So we had our formula. Sorry. Let's apply our force equation for a straight wire in a constant magnetic field. And just to make things really explicit, what we'll do is we will, you can imagine the wires going one way and the magnetic field's going another. We'll just tip our head so that the wire lies along the x-axis. The answer we get will be completely universal. You could get your answer and then at the end of the day, rotate your head back to the original position if you wanted. And so it'll give us something that we can write in terms of dx, which I think most of you guys will be more comfortable with, rather than leading with general arc lengths. So I'm going to have a wire. I'm going to take it to lie along the x-axis. Here. It carries a current. And then we're going to imagine that there's a uniform magnetic field. It's just going to point in some random fashion. The formula we get will be uniform, will work for any arbitrary magnetic field. And that's why this is a completely universal result. The formula we claimed for the magnetic force was I times the integral of ds vector cross the magnetic field. But if you think about it, the magnetic field has constant magnitude and constant relative angle between each little arc length differential. And what that means is that this integral, basically this multiplying by the magnetic field, could be done after performing the integral. It makes no difference because it's the same multiplication on each segment separately, which means you could kind of factor it out. And I should have said this. We'll let the wire have a length L. Well, so writing that down, that's going to be I times the integral of dx x hat, because I oriented it along the x-axis, and we'll say it's from 0 to L, cross the magnetic field. But the unit vector x hat is constant, so that doesn't have anything to do with the integral. And this becomes I times L x hat cross B. And if we go ahead and define this quantity to be L vector, to be L times x hat, and it points in the direction of the current flow, positive current flow, then I can write this as our final result. The magnetic force on a straight current carrying wire in the presence of a constant magnetic field is I L vector cross B. So that's a nice kind of compact formula. And to be honest, unless the problem says explicitly to derive it, this is simple enough that maybe you can just remember it. So what does that mean? Let's think about it. L points along the current carrying wire, okay, so it's to the right, and B is going to be going up. So in this case, I would work out L, curl my fingers in the direction of B, and the force would be into your eye. So this would give us a force which is perpendicular. It has to be perpendicular to both L and the magnetic field. So if the magnetic field is in the plane, going kind of diagonally upwards, and I is going this way, then the cross product is going to be into your eye. So the force would be into your eye. So that's just a dot with a circle. So the force on this guy would be into your eye. All right, so there's that. Notice if the magnetic field and the current were in the same direction, so if they're parallel, well, the cross product between parallel vectors is 0, so there'd be no force. So the force you get depends upon both the strength of the magnetic field, the length of the wire, the strength of the current, and also the angle. It is maximized when the magnetic field and the force and the wire is maximized when the magnetic field and the current carrying wire are perpendicular. So we'll see that later. Okay, so that's the general formula for a wire, a straight wire carrying a current in the presence of a uniform magnetic field. One last little example I want to throw in super quick is, what if it's not a straight wire? What if it's a wire which forms a loop? So what if let's say I have a wire that forms a loop. Okay, and let's say there's a current flowing in it, around it. And then let's imagine that there's a uniform magnetic field everywhere. So there are magnetic field lines. Just assume they are arbitrarily oriented, but evenly spaced, even strength everywhere. in which case my formula or my integral for the force becomes I times the integral. Now it's a closed path, so my integral is going to be a closed integral, and it's an orientable path of ds vector cross magnetic field. And again, because this is a constant vector field, it's the same cross product element by element, so you can factor it like this. And because it is a closed loop, when you add up all the displacements, this integral is going to be 0. And we see that the force, the net force on a loop carrying current in the presence of a constant uniform magnetic field is 0. If the magnetic field is not constant, then you can't factor it out, and then it doesn't have to be 0. But if it's a uniform magnetic field, that's the case. Okay, so I'll stop this video here. Next up, we will talk about what happens when you have not just straight lines, but you also have arcs.